All right, let's talk about electron donating and withdrawing groups. And so what we're going to focus on here is how to identify these groups, whether or not they're on this list, what effects they might have in chemical reactions, although our main focus will be electrophilic aromatic substitution. We'll mention nucleophilic aromatic substitution and Diels-Alder as well, and how these groups affect those reaction rates. But generally the principles we're going to look at are widely applicable. We'll even get into a little ortho-para direction for those electrophilic substitution reactions of benzene. So starting off, an electron donating group will donate electrons into a ring versus a standard reference compound. And so what we want to always do is define our reference as the compound that has a hydrogen in place of our donating group or withdrawing group. And so for this electrophilic aromatic substitution reaction, we'd have that substituted benzene versus benzene itself. And so what these donating groups will do, whether they have a lone pair or whether it's through hyperconjugation, they will donate electrons into the ring and push electrons toward the benzene ring itself. Okay, and so the effect that this has is it raises the energy of orbitals relative to the reference, and with the Diels-Alder, we remember the highest occupied molecular orbital can be raised. And so suppose we have a reference compound with that Diels-Alder that goes through, that has just the hydrocarbon, so we said the diene, so it just might be this reference. Well, if we were to measure the transition state energy, the rate of reaction is relative to this energy, and there it is. So we'd say delta G, the free energy of activation, the delta H, the enthalpy of activation affects the rate of overall reaction. When we put a donating group, it raises the energy of the diene, and sometimes we can even see it lower the energy of the transition state, maybe not, maybe it just raises this energy up and keeps the transition state roughly the same. Well, the net result is you have a lowering, a smaller value there measured from the compound with the donating group versus the transition state, and so you overall accelerate the reaction. So that was the effect on the Diels-Alder. But they also lower the transition state energy of any reaction that builds up positive charge in the rate limiting step, and that's electrophilic aromatic substitution. So if we have that transition state energy after we've added our electrophile, it would be relative to this carbocation. And so if we had a donating group on our ring, it can donate electrons into that system and stabilize that positive charge. Overall, the effect that it has versus the reference, so if we had a benzene reaction that went through this intermediate, it would lower the energy of this intermediate and raise to a bit the energy of that starting material, overall lowering the transition state energy, accelerating the reaction. Okay, and so what we would say is that electron donating groups are activators of these reactions where positive charge is built up at the transition state relative to that benzene reference compound there. So it's an activator. It speeds it up, speeds the rate up. Donating groups, however, would destabilize any transition state energy or intermediate energy where we have the, so here again, just to clarify, there's the transition state, there's the intermediate energy, making sure that we understand, due to the Hammond postulate, that the intermediate energy kind of follows whatever the closest species is in solution to that structure. And so with the intermediate lowering in energy, it lowers the transition state energy as well, thus lowering the rate. So back to our destabilizing group, it can raise the transition state energy where negative charge is built up. So if we have nucleophilic aromatic substitution and that transition state goes to an intermediate or a transition state where negative charge is built up, if we were to put a donating group on, what it would do is disproportionately raise, so here's our donated version, it would raise that transition state energy potentially and thus slow down the reaction. So the new transition state energy is slower, is greater, and so it would be a deactivator to nucleophilic substitution, these donating groups, because you're pumping too much air into an already full balloon is a good way to think about it, and it destabilizes that system. Now if we move on to withdrawing groups, relative to their reference compound, a withdrawing group is going to be able to withdraw electrons from a benzene system. And so I'm gonna kind of show how that looks here versus benzene. We might withdraw this pi bond up into a pi system in this withdrawing group, or it's a sigma withdrawing group as well as a case with halogens. So we can see that. We'll look at both of these scenarios, but it's going to pull electrons out of the balloon. And so what this tends to do is it lowers the energy of molecular orbitals relative to the reference compound, and in some cases this will accelerate the reaction. Let's look at when this occurs. So lowering the lowest unoccupied molecular orbital of the dienophile in a Diels-Alder reaction actually will accelerate the Diels-Alder by lowering the transition state energy. So what it does is, so we've got our reference here of our dienophile. We looked at the diene a moment ago, but if we take this diene, a file here with this electron with just the reference, so there's a hydrogen attached. If we were to attach a withdrawing group, it brings the energy down to where it more closely can interact with this highest occupied molecular orbital of the diene with the electron donating group. Okay, so when these two get very close together now, what it does, it lowers the transition state energy disproportionately and gets these guys together to be able to react. And so with the transition state, the new transition state here, the energy would then therefore be lower. Okay, so with the Diels-Alder, these withdrawing groups, when they're attached to the dienophile, actually accelerate the reaction. Now, if we look at withdrawing groups in terms of electrophilic aromatic substitution or nucleophilic aromatic substitution, they're on a benzene ring. And so when they are on a benzene ring where there's a reaction and negative charge is built up in the transition state, they actually stabilize the reaction. So if we have a nucleophilic aromatic substitution type scenario where we've got a leaving group on our compound and the nucleophile has added here, we are building up negative charge in the transition state, and then the next intermediate also would reflect that negative charge. So we'd have our nucleophile, our chlorine. It's a pretty unstable process to do this on its own. But if you were to attach an electron withdrawing group to this system, you could then pull those electrons, give them some place to go into that withdrawing system, and then stabilize that system. Net, what we do is we disproportionately lower the transition state. We put that withdrawing group, it lowers the energy of our system a little bit to begin with, but then it disproportionately lowers the energy of that intermediate, and thus the transition state energy is much lower overall than the original compound by stabilizing that negative charge. So we would say that withdrawing groups are activators of nucleophilic aromatic substitution. But if we have positive charge built up at the transition state or in the next intermediate of that rate limiting step, we're going to see that we are deactivating because it raises the energy of positive charge in that transition state. So net, what would happen as we got to that next intermediate with the positive charge, by putting a withdrawing group on, you enhance that positive charge and thus raise the energy overall, making that positive charge much worse, and that ends up slowing the reaction down. We would call an electron withdrawing group a deactivator of electrophilic aromatic substitution. Okay, so we got to pay attention to these groups. Now let's classify them quickly here relative to our reference benzene. So here's benzene, or any really this applies to any reaction where charge is going to be a major factor in the reaction rate. Hammett plots are one topic you can read more into on how these groups are used to elucidate mechanisms, but we'll get back to the groups themselves. Our first group here is the greatest donator. These are strongly donating. And so these are going to be the most powerful activators of electrophilic aromatic substitution. They benefit from a lone pair, whether it's primary, secondary, or tertiary amines, alcohol hydroxy groups. I'm naming the group based on not the functional group, but their actual group name here. So methoxy, isopropoxy for the alkoxy groups here. They're ethers, hydroxys, alcohols, amines. Just naming based on the groups. What they have the ability to do is donate into a system using their the full power of their lone pair. And so what we would see are contributors, resonance contributors, that would form, illustrating their donation of electrons into the ring. And with negative charge, we have 2 arrows per contributor to make sure we get them all. And this is really the source of ortho-para direction from a valence bond theory point of view. Molecular orbital theory has its own take on ortho-para direction. There are actually nodes in the highest occupied molecular orbital on the metacarbons, and so it disincentivizes reaction at those positions. But again, we have a good argument here based on valence bonds, so we'll use resonance to describe this, and we'll get all our contributors here. And then finally, we can resonate back to full aromaticity in that benzene. Remember, none of these contributors exist on their own. They are just a hybrid structure. Our final structure has all the pi bonds just moderately displaced by one carbon-carbon bond from where they started in the original contributor. So overall, we would show the resonance hybrid as having delocalization throughout the ring, partial bond here, and then partial positive in oxygen. It's losing some electrons so that it can donate here. And so notice, here's the ortho and the para positions have negative charge build up, and so they are most likely able to jump out and grab an electrophile in electrophilic aromatic substitution at those 2 positions. So there's the origin there of ortho-para direction. We'll talk more about that in a moment. Our second set here are moderate activators. We'll say moderately donating so that it applies to all reactions, not just EAS, moderately donating. Why are they moderately donating? Because that lone pair that's right next to our molecular orbital system of our benzene or our other system, depending on your reaction, you're competing with that lone pair for that lone pair with an electron withdrawing atom in a carbonyl here. So anything that we're having to share electrons with the benzene ring is going to not quite as strongly activate the system and donate into the system. So the same resonance contributors apply. We just have this additional resonance contributor that sends electrons to that negatively charged oxygen and just moderately donates rather than strongly. We still see ortho-para direction. So if we're keeping track here, we have ortho-para direction for both the strongly and moderately donating groups. Our alkyl groups, they are not going to donate by resonance in the pi system. They're going to donate by hyperconjugation. Hydrogen only has an s orbital, so when we're talking about a pi system, it's not going to be able to resonate per se through that pi system. Hydrogen can't because it's on the node of that pi system in the s orbital. But groups, carbon groups like alkyls, aryls, and alkenyl groups, alkyl just is methyl, ethyl, propyl, and so forth, they donate by hyperconjugation of their orbitals into that system. It's not so strong. It's actually going to be very lightly donating, and we'll call these weakly donating. Because you have to share with all the carbons that are bonded to those groups, okay? And so the pi system's not just directly free to donate into the ring. Aryls like to stay together. They like to just hang out in their aromatic system, so a little weakly donating there as well. The net result is, though, when you donate electrons into that system, there are no resonance contributors we can show here, but the net result is you accelerate the reaction relative to benzene if positive charge is built up. So we're still ortho-para directing here. Again, valence bond and resonance can explain ortho-para direction here. That's where we rely on MO theory, showing us where the charge buildup is, where the electrons are on that benzene ring in the highest occupied molecular orbital. So we're still ortho-para directing. With our next set here, we are now crossing the line to deactivation or withdrawing groups. So for EAS, it's deactivation. For nucleophilic aromatic substitution, you actually activate with these next groups because of the flip in charge at the transition state. We'll continue our discussion in terms of electrophilic aromatic substitution. So at this point, our withdrawing groups are going to be withdrawing relative to hydrogen, so they're going to slow down EAS reactions. But these are weakly withdrawing. Here we've got weakly withdrawing for our halogens. Because what's interesting about the halogens is that they withdraw. I'm going to show the bonds here so we can do this. Yes, they withdraw because they are electronegative. So they are sigma withdrawing. So if here's our sigma cloud, especially for fluorine, we would say that there's withdrawing going on toward that fluorine, just like we would with dipole moment and polarity, where we withdraw with the sigma system, but we are pi donating. So we still have resonance here that would show the same contributors for our resonance contributors like we show with phenol above, okay? The electron density is less. In fact, it's less overall than a normal benzene because the sigma system is withdrawing. So that sigma withdrawal has a greater effect than the pi donation. Ultimately, though, pi donation will still cause ortho-para direction when we react with these, but they do react slower than benzene itself. So deactivating due to they are withdrawing groups, but they are still ortho-para directing groups. They withdraw with sigma system with their electronegativity, but they pi donate with the lone pairs. All right, so we still get ortho-para direction. With our next set of groups, it's the flip around from what we saw with the moderate activators. These are our moderate deactivators. And the difference is now the pi bond is lined up to the benzene system so that instead of being nitrogen or oxygen first, we have the carbonyl first, so the net is to withdraw toward that oxygen. Okay, so these are aminocarbonyl groups. These are primary, secondary, or tertiary amides here. So hydrogens can replace those R's or alkyl groups, esters, carboxylic acids, and halocarbonyl groups, so acid halides there. These are just the group names for each of those. So they're moderate deactivators. At this point, though, look at the resonance now. We've changed our pattern to where we're putting positive charge into the ring through the pi system. And so now, as we resonate, all those positions before that had negative charge are now getting positive charge. And so we end up deactivating these positions, and now we are officially in our meta directors. So we are now going to direct away from these orthopara positions that are taking on positive charge Again, that's a valence bond theory construct. We would see just greater density in the meta position in our molecular orbital calculations here. If we were doing this in, oops, sorry, these carbon right there. And in this final contributor, we would see that carbonyl reform as well, so make sure we get that. And there we go. So we're back, except for the placement of the bonds in the benzene ring, we're back to where we were before. And so ultimately the hybrid structure then, delocalized bonding throughout all these areas here, and then we'd have delta plus, delta plus, delta plus, blocking the orthopara positions, leaving those meta positions as the areas with more electron density. Okay, so meta directors. Same goes for our strong deactivators. So strongly deactivating. And I guess to keep it general, I should say moderately withdrawing and strongly withdrawing, because nucleophilic aromatic substitution is going to be greatly accelerated by these groups. So the strong withdrawers actually accelerate nucleophilic substitution. They deactivate, decelerate electrophilic substitution. And they are our cyano groups. So nitrile, benzonitrile here, okay, has a pi bond that can withdraw to an negative nitrogen, so there's that. The sulfonate or the sulfonic acid here, so we'd have two SO bonds here that can withdraw into both of those, so that's strongly withdrawing. We have our ammonium ion that is sigma withdrawing, because if it's an NH3 plus or secondary, tertiary, that's not going to withdraw through resonance. It's going to withdraw through that positive charge directly next to the ring as a sigma withdrawing. It's still strongly withdrawing. Meta direction still applies. And then finally, the nitro groups have this structure, and they withdraw into that nitrogen as well, okay, or into the oxygen of the nitro group. All right, the most electronegative element. All right, so there's our summary of activators, deactivators, but more importantly, donating groups and withdrawing groups. And orthopara direction occurs for strongly donating, moderately donating, weakly donating, and weakly withdrawing for orthopara direction of electrophilic aromatic substitution, and then moderately and strongly withdrawing groups meta direct for that reaction. But again, your individual reaction determines whether it is an activator or deactivator, as we have discussed.